So this lesson that finishes chapter 1 for us was the last lesson you learned in Ham last year. Okay, this is the very last thing that Mrs. Cragness worked on with you last year, having to do with limits, having to do with limit quotient. There was a lot of subtraction and a lot of working out, okay? And so that was, she was laying the groundwork for what you were gonna need for that calculus. That was literally the last pre-calculus thing you did. So we're gonna define rates of change and something called sensitivity. People, oh, you're so sensitive. Okay, so we'll have to figure out how sensitive our graphs are, but we're gonna define rates of change today. And this will finish up for us chapter 1. There are two kinds of rates of change. There's a rates of change called an instantaneous rate of change. There's also a rate of change called an average rate of change. The difference is the length of time that occurs when we're figuring that out. An instantaneous rate of change happens in the fraction of a second, okay? And an average rate of change is happening over a longer period of time, okay? So we're gonna distinguish, you gotta know the difference because it's gonna change the formula that you use. Okay, and we'll do a little physics with velocities, see how this connects to physics. All right, so here you go. By definition, the average rate of change for a function is the amount of change that occurred divided by or over the length of time that occurred, okay? The amount of change divided by the length of the interval, all right? So that is important for you to know, the amount of change divided by the length. Now, over the historical years of math, change has been always signified by the Greek letter delta. So you would see this is a delta. And they would define it as delta, maybe of whatever you're measuring. So the change in your weight, that would be delta W. Or the change in your height would be delta H. Okay, so we use the Greek letter. Now, if we're talking about over the amount of time then, so divided by, okay, what do you think the denominator is? Delta T. Okay, very good, very common for it to look like that. Okay, delta W or delta whatever over delta T. Okay, now to find the change in any two things, you just have to subtract them. Okay, to find the change in your height over your lifetime, you need to know what your height is now compared to what your height was when you were born. And you subtract them. It's always done, a change is always done by a subtraction. So this would look like a W2 minus a W1. Okay, your weight, your second weight minus your first weight. And this would be over a T2 minus a T1, okay, over the first time minus the second time. But the variables are irrelevant, okay? We also can see this as a y2 minus a y1 over an x2 minus an x1. And now you're starting to think, wait a minute, I've seen this before, okay? Yes, this is the definition for slope. The average rate of change is the same as what we call the secant slope. Okay, now up to this point, you only ever knew just of one kind of slope. We just called it slope, but there are two kinds of slope. Slope is distinguished. There's a slope that's called the secant slope, and there's a slope that's called the tangent slope. All right, so let me show you the difference. Just draw a nice little gentle curve, maybe. Has a little bit of a curve to it, not too much. The secant slope is what you've learned before. The secant slope connects two separate points, one to the other. Okay, so that is called the secant slope. And we've defined that in the past as y2 minus y1 over x2 minus x1. And what single letter have we used to associate with that? M. Okay, that is called the secant slope. So here I'm today to tell you that there's another kind of slope. Okay, because the secant slope is always a straight line. But in calculus, we want to talk about what is the slope on something that's curved, not something that's straight. Okay, so the other kind of slope would be the slope that skims off and just touches one point and then leaves the curve. Okay, and that kind of slope is called a tangent slope. All right, so that's the difference. One is a secant slope, which requires 2 points, and a tangent slope only requires 1 point, which means it needs a whole new formula, because the whole premise of the formula of secant slope is you needed 2 different points. You needed a point A and a point B, and you had to be able to subtract them to figure out your slope, your rise over run. A tangent slope only needs 1 point, which is what made the birth of calculus so revolutionary and so countercultural to what anybody had ever thought about before, because everybody had thought so literally about slope, that slope had to be 2 points, one connected to the other. And Isaac Newton comes along and Gottfried Leibniz comes along, and they're working on it. They're like, nuh-uh, we can do slope on 1 point. Okay, watch us. And then they proved it to the world that they could do it. And that's where we got calculus from. So that's what we're going to talk about, the difference between those 2 things today. All right, but let's start baby steps. Let's start with the average rate of change. Okay, the average rate of change is regular old slope, just the way we always have known it. Okay, so from now on, I'm not going to call that slope. I'm going to call it the average rate of change, but the formula is still the same. Okay, so we know that this is a parabola. We're connecting point from -2 to the point of +4. We just need to know what their y values are. So we first want to figure out what is the f of -2. And so we plug -2 into that. So 2 times -2 squared minus 3 times -2 plus 7. So that'll be 8 plus 6 plus 7. So if I'm doing my math right, 21. Okay, then we want to know, that's the beginning. Now we're going to connect this to f of 4. Okay, so this will be 2 times 4 squared minus 3 times 4 plus 7. So that's 32 minus 12 plus 7, so 27. And so now our average rate of change is y2 minus y1 over x2 minus x1. In other words, f of 4 minus f of -2 over 4 minus -2. So it's just y2 minus y1. It's the old way of figuring out the slope. So this would be 27 minus 21 over 4 plus 2, or 6 over 6, which is 1. Okay, so the average rate of change, also known as the secant slope, turns out to be 1 here. Any questions on that? All right. Okay, so now just for something different, draw your curve going this way. All right, if this is point A, then its y-coordinate is f of A. If this is point B, then its y-coordinate is f of B. And the slope that connects those 2 things is f of B minus f of A over B minus A. All right, how do we then find the slope of the curve? Okay, so now we pick any point between those 2 on the curve. It can be, doesn't matter on what end it is, any point you want. You can pick it right in the middle. If you just like the symmetry of it, it does not matter. Okay, we're going to call that f of x, or x. And so then it's, what's its y-coordinate? F of x. All right. Now, if you could zoom in and find the closest point to that. Now, I know that's not possible, because we can always squeeze these closer and closer. But if you could zoom in and find the next closest point, so close that there wouldn't be any space in between them. Okay, how do you define that so it's still distinct from x comma f of x? And we define that as x plus h. How big do you think h is? Okay, h is very small. In fact, h is approaching what number?
0.
Correct. Okay, that's x plus h. So what's its y coordinate? F of x plus h. And what would the slope that connected those two things, how would we define that? F of x plus h, that's y2 minus f of x, which is y1, over, well, you're jumping the gun here a little bit, over x2 minus x1. But we have to be careful about that because h is so small, and we have to specify that h is approaching 0. Now, you guys were right. The denominator does simplify to the plain letter h. But what's the one number that h can never be?
0.
H can never be 0. So that's why we need the limit in front of it to say, I know h can never be 0. H is going to approach 0, and it can approach 0 from the minus side, and it can approach 0 from the positive side. We have a two-sided limit going on here, but h will never actually be 0. It will just be close to 0. And this is how you find the tangent slope at a single point. Okay, you pick the 2 points that are so close together that you can't tell the difference between them, and you say that the limit of the distance between them is approaching 0. All right, so the slope of a curve. In calculus, we want to define the rate, okay, that's our vocabulary word here, at which the value of a function is changing with respect to x at any value of a single a. Okay, any value, not needing an a and a b, but a single value a to be the slope of the tangent to the curve. Okay, so all these words, rate, slope, tangent, okay? And we define this to be the instantaneous rate of change because it's happening in a fraction of a moment. The amount of time that has gone by from one point to the next is almost immeasurable. It is so small. And so we call that the instantaneous rate of change. Okay, any questions so far? All right, so let's actually do the math. Okay, so here's a parabola. The parabola is x squared plus 2. Let's just picture what this parabola looks like. Okay, here is a little parabola. And I am finding it at the point -1, which is about right there. So I need to know what f of -1 is. I need to know its y value. So I go ahead and I plug that into the equation, -1 squared plus 2, that works out to be 3. I am going to pick the point microscopically close to that so that I can find the instantaneous rate of change. So when I zoom in, I will pick this point that's sitting right there. That is -1 plus what?
H.
Plus h. Okay, so now I want to know for that point, what is f of -1 plus h? Well, that's going to be -1 plus h quantity squared plus 2. Now that's not going to work out to 3. That's going to work out to something else. I actually have to do a little FOIL to work that out. When I FOIL, I will get 1 minus 2h plus h squared plus 2. Okay, that's what that works out to be. So now if I'm going to find the instantaneous rate of change, okay, I am going to find f of negative 1 plus h minus f of negative 1 over negative 1 plus h minus negative 1. And I'm going to do the limit as h approaches 0. And so I'm just going to take the y values I just found, and I'm going to simplify and do the math on this. Okay? The denominator is always going to simplify down to plain h. As long as you're doing the algebra, you keep the limit going. So f of negative 1 plus h turned out to be 1 minus 2h plus h squared plus 2, and then minus 3, which was the other y value, so I'm subtracting those two, and the whole thing is over h. Okay, what happens in the numerator? Okay, so 1 plus 2 minus 3. Those are all gone. Okay. Algebraically, the next step is to factor, because the numerator has a term that's negative 2h, and the numerator has an h squared, so what do they have in common? Okay, so I can factor out an h, leaving me with negative 2 plus h in parentheses over h. Once I've factored out, then I can reduce, and I'll reduce my h's. Is there any other algebra to do? As soon as you're done with algebra, then you can drop the limit notation and put the value of 0 in, and the answer is negative 2. That instantaneous rate of change of negative 2 tells me what the instantaneous slope was. Does that make sense to you, that the instantaneous slope that's coming right through those points right there is a negative 2? Does it look like it might be about negative 2 at that point? Will it ever be negative 2 again? Is there any other place on this curve that would have that same slope? No. No other slope will ever be negative 2 again. It's an instantaneous value. Okay? Because the slope that's up here is not negative 2. It's a negative something, but it's not negative 2. And the slope right here, what's that slope? 0, okay? And then once you turn the corner, what's the slope right here? What kind of number is it? It's a positive. Now it changed to positive. So it will never be negative 2 again. It's only negative 2 at that one instant moment. All right, let's try another one. Find the instantaneous rate of change for the volume of a cube at 3. Now there's no equation here to work with. You're going to have to make your own equation. Okay, your equation for the volume of a cube is x cubed. Okay, hopefully you all know that. Okay, the volume, depending on x, is going to be x cubed. So we need to find v of 3, and we also need v of 3 plus h. So we need 3 itself, and we need 3 plus h, which is super close to that. So the volume at 3 is 27, but the volume at 3 plus h is 3 plus h cubed, which is not simply 27 plus h cubed. That's not how cubes work. Okay? Rather, it is 3 plus h times 3 plus h times 3 plus h, which gives you 27 plus 9h plus 3h squared plus h cubed. Okay, so it's a lot more to it. Okay, so you just cube it out. Then, now we're ready to find the instantaneous rate of change. So the instantaneous rate of change would be the limit, and don't forget the limit. The limit is what makes it instantaneous. If you don't put limit on there, then h could be 0, and then everything falls apart because you in your fraction. So we would have a v of 3 plus h minus v of 3 over 3 plus h minus 3. So the denominator is always going to simplify down to just h. And my numerator would be the 27 minus 27 minus 9h minus 3, oh, whoops, I'm going the wrong way. 27, whoa. 27 plus 9h plus 3h squared plus h cubed minus the original 27 and the whole thing over h. So what happens is that the 27s reduce away, and I forgot my limit. Don't do as I do, make sure you remember your limit. And then we factor, and then we reduce. So the pattern becomes very similar each time. We're going to factor out an h, which would give me 9 plus 3h plus h squared, all over h. Then I can reduce the h that I factored out, and then I can be done with algebra. And the algebra then allows me to plug 0 in, so I'll get 9 plus 0 plus 0, or 9. And so the instantaneous rate of change at this moment is 9. Will it ever be 9 again? No. Okay, it will never be 9 again. It's only 9 at this instant. Okay, here's our last algebraic one. Okay, find the instantaneous rate of change at 1. It's usually the algebra that's going to mess people up. Okay, it's not usually any of the reducing or things like that. It's the algebra. Okay, so we want to know what y of 1 is, and we want to know what y of 1 plus h is. Y of 1, who's got that value? If you just drop 1 right in there. 0. Okay, y of 1 plus h would be 1 minus quantity 1 plus h all over 1 plus h. What will that simplify to be? Okay, the denominator I'm going to buy is 1 plus h. I want you to think about your numerator, though. It's negative h over 1 plus h, because that negative in parentheses has to affect both of those. All right, so if I'm going to find my instantaneous rate of change now, my limit will be negative h over 1 plus h minus the other y value, which was 0, all over h. The 0 is not going to affect my problem at all. So I'll have negative h as my numerator, 1 plus h is my denominator, and then I don't want another denominator yet, so what algebra do I do? Multiply by the reciprocal, which would be 1 over h. Okay, that's always better to multiply by the reciprocal. Then I can reduce. But make sure that you don't drop that negative, that you don't neglect that negative there. So I will have the limit as h approaches 0, the numerator is negative 1, the denominator is 1 plus h. And now that my algebra is all done, all my reducing, all my combining like terms, my FOIL, my multiplying by the reciprocal, now the algebra is done, then I can plug in 0, and I get negative 1. So the instantaneous rate of change, which means the slope at this instant on this hyperbola, is negative 1, but will never be negative 1 again. All right, in physics, we call this velocity. The math is the instantaneous rate of change. The word in physics is velocity. Words like how fast, speed, okay? So that leads you to just understanding vocabulary. That things like the slope of a curve, the rate of change, the instantaneous rate of change, the velocity, all of those words, okay? And I could throw on there how fast. I could throw on there what's the speed. All of them use this exact same difference quotient there. They all mean the same thing. Okay, so when in doubt on this homework assignment tonight, they're probably asking you about this. The only time you would not use this is if the specific word average was in there. And if the word average is in there, then you go back to the old definition of slope, which required two distinct points that were separate from each other. But other than that, the vocab is all this. Okay?